Thank you all for coming to Katie Kirk's dissertation defense. I'm super excited to introduce Katie. We'll be presenting her dissertation research. I'll let her discuss all the things that she's going to talk about today. So I won't get into any long discussion about that. Just to introduce Katie, she's an oceanographer with NOAA. Okay, lots of different affiliations with the National Ocean Service, Center for Operational Oceanographic Products and Services Co-ops, and the Coastal and Estuarine Circulation Analysis Team. CCAT is what you guys call it. Lots of affiliations since 2016. Katie's basically working on her Ph.D. under a NOAA Advanced Education Program work study thing since the fall of 2018. And we appreciate the support from NOAA, NAS, co-ops, and all the people associated with it. That's been really great. She got a BS in Earth Sciences with a concentration in Ocean Sciences from Cornell, and a Master's of Engineering in Ocean Science and Technology from the joint Cornell-Woods Hole program. I want to introduce the committee for a minute, myself as the lead committee member. Greg Dusek, online, senior scientist from NOAA, NAS, and co-ops down in Silver Spring. John Kelly, also with NOAA, Coastal Marine Modeling Branch, Coastal Survey Development Lab, NOAA, NAS, blah, 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 blah. He's a meteorologist, does lots of things with them. He's also a faculty member in the Center for Coastal and Ocean Mapping. Diane Foster, Director of the School of Marine Science and Ocean Engineering here at UNH, faculty member at OE and ME. Jamie Pringle, Professor of Earth Sciences and the Ocean Processes Analysis Laboratory at EOS. Also with lots of affiliations, and Tracy Mandel, professor in mechanical and ocean engineering. Okay, so the format for today is Katie's going to talk for 35 or 40 minutes, whatever, and then we'll take questions from the general audience, and then including those online, and then when that's all completed, we'll have a closed-door meeting with the committee. Okay, thank you and welcome, and Katie, please.
Okay, thanks, Tom. Thanks everybody for coming, those who are here in person and those online. If I start to get quiet and you can't hear me in the back, just wave your hand. Yeah, exactly. Yeah, Andy won't be shy. So I'm going to be talking about the potential vorticity dynamics driving variability and mean tidal currents flowing through bounded estuarine channels. I'm going to start out with an overarching research goal, my motivation, and then I'll get into the nitty-gritty of chapters 1, 2, and 3. Finish with some key conclusions, implications, and then I'll take questions. Starting out, the research goal is to study spatial and temporal variability of mean tidal currents flowing through narrow estuarine channels. By tidal currents, we're talking about the flow driven by the tidally induced pressure gradient at sea level, and by the mean flow, we're talking about the average taken over several hours. For spatial variability, we're talking about variability in the horizontal. So most of this flow that I'll be talking about will be depth averaged. There's very well mixed environments with very little variation in depth. So the depth average flow is very representative of the velocities here. So our spatial variability is in the horizontal. And finally, the temporal variability, these are oscillations that are happening on the order of several minutes. So it's happening more frequent than our mean tidal currents. So this is high frequency variability relative to that mean tidal current that we're interested in. So here's a spectral energy scale relative to frequency and period on the x-axis, where at NOAA and co-ops, we're obviously interested in tides and tidal currents that happen on the order of semi-diurnal to diurnal time periods, so several hours to a day. And the motions that we're interested in are the high frequency variability about that mean current that fall in the infragravity to far infragravity band, which is on the order of hundreds of seconds to tens of minutes. So in chapters 1 and 2, we're looking at tidal currents flowing through narrow estuarine channels that can have really strong horizontal velocity gradients in the along channel velocity. So these are two examples, one in the Piscataqua River and one in Hampton Inlet, both estuaries in New Hampshire. And we have a really strong cross-channel gradient, so in the x direction, moving also in the x-axis of the along channel velocity, v. And so that strong cross-channel gradient in the along channel velocity is called shear, and it's denoted by v sub x here. And you can see that arrow of how quickly those velocities change over a relatively short period, leading to that strong shear. And here in the Piscataqua, it has a really strong gradient relative to the Hampton Inlet has a relatively weaker gradient when comparing the two. So we hypothesized that given a steady mean flow with some strong horizontal gradient and that along channel velocity, a small perturbation in that flow can lead to instabilities in the mean flow that can cause a meandering of that mean tidal current. So again, these are horizontal motions. You can kind of think of a snake in the grass here. And ultimately, the meandering and the instabilities can lead to the spin-off of eddies and vorticities. And things can go into turbulence. So in order to picture this in a more familiar way that we've all seen, where the flow goes from steady mean flow to turbulence. Tom might have experience blowing out a few candles yesterday. Happy birthday, Tom. So here we have obviously stable flow near the wick. It becomes unstable, goes into turbulence. We're really interested in the unstable portion where things are still in the linear realm. So we're not worried about the turbulence yet. It's more of an implication. So for chapter 3, we're really interested in the spatial variability of the tidal current. So this is an idealized cross-section of flow down a river where we expect the max velocity to happen or occur near the surface and near the middle of the river, where there's less influence from bottom friction and sidewall friction. And we can see that in Hampton Inlet, actually. It's a relatively U-shaped bathymetry, pretty simple, and the fastest currents happen near the center of the channel and near the surface. However, for chapter 3, we're looking at an area that has a bit more complicated topography and bathymetry south of CV Island and the Piscataqua River, specifically looking at this transect south of Henderson Point. So here we have a shallow shelf, and as we're moving south down that transect, we drop off into a deeper channel. And we may anticipate that the currents are faster in that deeper channel, where again, there's less influence from bottom friction. However, observations from Littman and Wozniak pretty much show the opposite. The currents are faster over that shelf on both the flood and ebb. So for chapter 3, we're really driven by this question of what's going on. Let's figure out the forcing dynamics causing this. So the summary of my goals and objectives, the first 2 chapters, I'm looking at the temporal variability of mean tidal currents. The first chapter is a theoretical analysis. The second chapter is observational. And my objective in chapter 1 is to complete an analytical linear instability analysis. For chapter 2, I'm observing these motions and then going to compare that spectra to my predictions from chapter 1. For chapter 3, I'm looking at that spatial variability of tidal currents, doing this numerically, and then I'm going to, or the objective is to determine the forcing mechanisms driving this observed velocity intensification. So any spatial or temporal variability in the mean currents will have implications on the fate and transport of organic and inorganic matter. So here we have just an example of an oil spill on the left, and then on the right, it's actually a picture I took in the Delaware Bay doing field work. And you can see plastic and particles and marine debris kind of all clumped up together. So obviously the fate and transport under steady currents would be slightly different than in an unsteady environment, especially if turbulence and mixing is involved. Secondly, we have tidal energy resource assessments and renewable energy initiatives. Here at UNH, obviously, we have the Living Bridge initiative, where there's tidal turbines, and I'm sure that there was a lot of effort put in to figure out where best to place that turbine across the river, given the spatial variability of the tidal currents, to figure out where can they harness the most energy. And so if there's spatial variability or even temporal variability, that will impact how much energy that they can harness. Last but not least, obviously my office at NOAA, our primary goal is to produce products to help ensure safe navigation, especially in a time where ships are continuing to increase in size, limiting our maneuverability. So understanding that temporal and spatial variability can help us better produce products to help, again, ensure safe navigation and support our mission here at NOAA. So I'm going to dive into each of the chapters, starting with chapter 1. Just a reminder, the objective is to derive the dispersion relation for linear barotropic instabilities of tidal currents over simple but variable inlet geometries and bathymetries. So to give some background, Nealer and Mizak in 1971 looked at non-divergent barotropic modes that combine to form oscillations off the western part of North Atlantic. So you can think of the Gulf Stream oscillations. And Bowen and Holman then modified that analytical solution to be more applicable to the nearshore. So they are ignoring Coriolis and they're rescaling the motions to be applicable for longshore current oscillations. And they found wavelengths on the order of hundreds of meters, frequencies that fell into the infragravity and far infragravity band, and phase speeds that were on the order of a third of the max velocity, and these were progressive motions moving in the direction of the mean current in the longshore direction. And then Dodd added to this by adding a linear bottom friction term to this analytical analysis. A lot more has been done, but these are just the core studies that we're working off of. So here, we're going to apply similar methods, but we're going to do so in an estuarine environment where our currents are primarily driven by that tidal-induced pressure gradient in the sea level and not by the incident gravity wave forcing in the near shore. We are going to be in a bounded flow situation, so obviously on the continental shelf and the near shore, you have that infinitely extending boundary out to sea. Here, we're bounded on both sides. And we're going to have variable bathymetry and inlet geometry. And this is going to allow us to have a more generalized solution that we can apply to a wide variety of different channels and inlets. And we do include a linear bottom friction like Dodd. So to begin with, again, just a reminder, we're looking to solve for the scales of motion here for these instabilities. And we have a key assumption is that these instabilities are growing in time. So we have a complex gradient frequency that has a real component and an imaginary component, and we're giving our solution real wave numbers. I'm going to basically, spoiler alert, show you the solution here, what it's dependent on, so it'll help me explain this moving forward. So the radiant frequencies will be a function of the wave numbers and also the cross-inlet velocity structure. So again, you can imagine moving across that idealized transect of an inlet, and you have some velocity that's near zero towards the boundaries and has a max velocity towards the middle of the channel and then degrades back over to zero. And where that maximum velocity occurs, we can toggle back and forth with this delta parameter. So if we push it over to 0.2, we have a really strong shear in region 1. If we leave it in the middle, we've got a symmetric shear, and then we can push it back over to 0.8. So this is, when I'm talking about delta and moving it over, this is what I'm talking about, of changing the strength of shear in each region. We can also change the inlet widths. So for the remainder of this talk, I'm going to leave the width of the non-zero current, so X naught in regions 1 and 2, I'm going to leave that alone. And all I'm going to be changing is region 0 and 3 widths. So I'm making the inlet either wider or narrower. I can also change the depths, and I'm also leaving the total depth in regions 1 and 2 the same and alone, so it'll be equal to the total depth. And I'm just changing the shoals on regions 0 and 3 to be shallower or deeper. And then I'm adding in a friction term, which suppresses the flow. So my solution is a function of all of these terms, which means it's very generalized, and we can change all of my velocity structure and inlet geometry to then modify and replicate other channels and inlets. So in order to derive our solution, we have a couple assumptions about the flow. The first is that the total flow is a combination of the mean flow, which is capital V, and a small perturbation, which are the U prime, V prime. The flow is steady, and we're linearizing around the perturbation velocities. We're neglecting Coriolis force because our characteristic unsteady frequency is much larger than our Coriolis frequency. The flow is incompressible, non-divergent. So we can reduce down our continuity equation and introduce a stream function. The channel is infinitely long. There's no flow through the inlet boundaries, and we're neglecting a horizontal eddy viscosity. So that brings us to our depth averaged horizontal momentum equations. We have acceleration terms on the right-hand or left-hand side, forcing terms on the right-hand side, which, that sounds a little bit like F equals ma, it's just written in cursive for you. Okay. So we have acceleration, our tidally induced pressure gradient with a bottom friction that we parameterize with a linear coefficient. And again, we have incompressible flow, so we can reduce our continuity equations. So here are our equations of motion. We can introduce a stream function to represent our velocities, which we can then plug into our cross-differentiated momentum equations to get down to this equation. We can then rewrite that in terms of the linear potential vorticity, and this is really our governing equation here. And our potential vorticity is made up of the relative potential vorticity, which is dependent on the curl of the perturbation velocities, and the background potential vorticity, which is dependent on the shear of the mean current. And you'll notice the right-hand side of the equation does not equal 0 because we included a linear bottom friction, so it's not conserved. So here's our governing equation. Now we need to assume a solution, which we assume is wave-like in form, and it's propagating in the along channel direction. Test this out in the y direction. And again, we're assuming that these motions are becoming unstable in time. That gives us a phase speed that's made up of the real component of the radiant frequency and the wave number. We're solving for initial growth rates, so our time is 0. And we have two key assumptions. One's that the stream function is continuous across the inlet, and the other's that the sea surface elevation, which is eta, is also continuous. So we apply a bunch of matching conditions, and ultimately we get down to the third order solution here for the radiant frequency, which again is a function of all of these variables. We have two key determinants of whether unstable modes can occur. One is that there's a positive imaginary radiant frequency, and if that's the case, then these motions are growing, are becoming unstable exponentially in time. The second is that we have an extremum in the background potential vorticity. Here we have two extremums based on our velocity structure per region, and we've broken this down into 4 regions, which gives us that the two extremums. And basically, this just means we have the possibility of unstable flow due to the shear on either side of that max current. So this is what some of the solutions look like given a velocity structure shown above, where we have a flat bottom, we don't have any friction, and our shelf widths are 20% of the total inlet width or channel width. So we have growth rates that fall into that infragravity and far infragravity band that's on the y-axis, you can see, and the associated wavelengths that are on the order of hundreds of meters. So these are the unstable modes. And again, we're looking at how the unstable modes change with changes in shear. So the legend in that left plot is associated with changing the shear across the channel. And you'll immediately notice that it's symmetric in that a delta of 0.1, so if you were to push this over even more, gives the same growth rate as a delta of 0.9. So if you were to push this over a little bit more. So it doesn't matter if the shear is strong on the left or the right-hand side of the inlet, the growth rates will be the same. And we're really interested in the fastest growing mode, which is the extremum of this growth rate and the associated wavelength, which again, those motions fall into the scales that are consistent with what has been previously predicted in the nearshore environment. So this is Bowen and Holman's solution, which has a very different velocity structure. As you can see above, it has that seaward extending boundary, and it's up against the surf zone. So that's why it doesn't have another region ahead of that velocity max. And so you'll see that the solutions in the nearshore are not symmetric in that it really depends on the seaward shear. If you push that shear over to the seaward side of a 0.9, you're going to get a faster growing mode. Both of these have phase speeds on the order of 1/4 to 1/2 of the max velocity. So they're very consistent with one another. We're actually able to boil our cubic solution down to the quadratic by changing the inlet parameters. This was a nice check on our solution to make sure that our solution was correct. So now we can walk through what each of the parameters within the function of the solution, how it affects the solution here. So we have our growth rates on the secondary y-axis and our wave numbers on the primary y-axis. And here we're changing the shear, which again, we're pushing that where that max velocity occurs across the channel. As you can see, if you have a symmetric shears in the middle case, you're gonna have the slowest growth rates, 0.5. Slowest growth rates and the smallest wave numbers. And if you increase the shear, you're gonna have a faster growth rate and larger wave numbers. Here we're making our shelf widths wider, and as you do that, you're gonna have a faster growth rate and larger wave number. If you make the shelves go deeper, so you're nearing a flat bottom, then you'll also have faster growth rates and larger wave numbers. And finally, if you add in a friction, this actually doesn't impact the wave number, it only suppresses the growth rate. So you can imagine this, when you're looking at this plot here, we're looking at growth rates in the y-axis versus wavelength in the x-axis, and we're just increasing the friction, and you can imagine that curve just being pushed down. So the range of unstable wave numbers decreases, but the wave number associated with that fastest growing mode doesn't change. It's just that the growth rate gets suppressed. So here we can see the progressive nature of these instabilities, with the stream function on the left-hand side, they're progressing in the long channel direction, and the right-hand side is that total velocity. So that mean current plus that small perturbation does indeed lead to the meandering of that mean flow. And for implications of this, if there's presence of instabilities, there's likely a mixing of momentum horizontally, and we can calculate this through a Reynolds stress. So we're calculating the along channel momentum in the y direction that's mixed across the channel in the x direction. And we can do that for different inlet geometries, and what we see is that under a non-zero Reynolds stress, we expect mixing. So when SYX is high, we expect a lot of mixing, which occurs under areas of really strong shear. Also slightly larger shelf widths and deeper shelf depth. So again, nearing that flat bottom. But you'll notice the shear, that scale is different from the other plots. So the shear is the really dominant term here. So strong shear leads to instabilities that could lead to mixing of momentum, which could have ecosystem implications. So in conclusion for chapter 1, we did solve the third order dispersion relation for linear barotropic instabilities over simple but variable inlets and bathymetries. Solution is general. In that sense, we can apply it to a wide variety of estuaries, and it's collapsible to that nearshore solution. We found consistent wavelengths of orders hundreds of meters, growth rates in the infragravity and far infragravity bands, and phase speeds on the order of a third of the max velocity, and these motions are progressive in the alongshore direction. And the fastest unstable growth rates and the widest range of wave numbers occur when the currents are bounded, so not in that nearshore solution, with wider inlets, stronger shear, and again, shear is really the dominant term here, over a flat bottom and with inviscid flow, so when friction is not suppressing the velocities here. And the implications of this is that instabilities can cause horizontal mixing of momentum under that non-zero Reynolds stress. Okay, so now we're going to move on to chapter 2, where we actually observed these shear instabilities in Hampton Inlet. From this picture, we have the ocean behind us, and up to the right is north, and down to the left is south. I wanted to show this because you can see that the flow is bounded by these jetties, and that southern jetty does get overtopped during high tide. We can also see some incident gravity waves coming in. For the most part, the incident gravity waves are attenuated due to shoaling and refraction by the time they reach the inlet. However, there is some wave breaking on that southern side of the inlet. So our objective here is to observe the instabilities and compare the estimated wave number frequency spectra to the linear solutions. Just giving some background, Altman, Shea et al., and I will say et al., Peter Hout is part of this et al., so you can correct me if I misspeak here. We're the first to observe this in the nearshore in the 1986 superduct experiment using a spatially lagged array of current meters. And they found motions on the orders of hundreds of meters in this far infragravity band, and they were too slow to be considered low mode edge waves. So the significance here, we're applying very similar methods, but again, we're doing it in the estuarine environment where the current is really driven by the tides. It's not driven by the incident gravity waves driving that longshore current. And this is really important because we're really hypothesizing that the instabilities are from a perturbation in the shear of the current and not from gravity wave group forcing. So we collected a lot of data. We did some cross-channel ADCP transects with the Zegoboat along these 4 red lines, and that gives us a sense of the spatial variability of the tidal currents. We then collected some sonar and GPS data to splice together this bathymetry, which is shown in the contour plot. And then finally, we deployed a spatially lagged array of 7 stations made up of ADCPs and ADVs, deployed along approximately the 3-meter depth contour line for about 6 days, which covered 12 tidal cycles. And we primarily used a 1 Hertz sampling rate, except for the Sontect, which measured once every 10 seconds. And then we had a minimum lag spacing of 18.5 meters between stations 4 and 5. And this sets our maximum wave number we can directly observe. The total length of the array was 389 meters, and this sets the maximum wavelength we can directly observe without using iterative maximum likelihood estimators. So 2 key assumptions. We're assuming that the flow is stationary during our runtime, so in time, and then it's coherent along the array. So homogeneity and coherency are really important here. So if you have a really long array, you're likely to not meet those 2 assumptions. So you sometimes have to shorten your array in order to meet the coherency assumptions, but then your wavelengths will be longer than your array. Your wavelengths of interest that you're trying to measure will be longer than your array. So the iterative maximum likelihood estimators allows you to actually estimate wavelengths that are longer than your total length. Here's the UNH Zegoboat. So a big thanks to John Hunt. I don't think he's here, but John Hunt helped us in this fieldwork. We collected GPS data on the low tide and sonar data on the high tide and spliced them together to get that bathymetry data. And then the Zigoboat is also equipped with ADCP bottom tracking, which we collected the cross inlet transects with. Here's a schematic of what it looked like to attach an ADV in this case to the pipes, which we jetted into the seabed. Hampton has a pretty large tide range, 3 to 4 meters. So this picture was obviously taken on a low tide. And a big thank you to everyone who helped. I think Savannah and Melissa were here, Josh, Jang, John. There was a big group of us, so thank you everybody who helped us both deploy and recover these sensors. So this is what the ADCP transect data looks like on a flood case, which is on the left, and an ebb case, which is on the right, relative to our sensors, which are red, the red dots. And you can see on both the flood and ebb case, along the northern and southern edges of the transects, we have strong shear, or that cross-channel gradient in the along channel velocity. So it sets up nicely this idea that instabilities may form. So here we have station 3, which is sort of in the middle of our array. We're looking at the time series during the full deployment period. The top plot is our water level, which is derived from the pressure sensor. And again, you can see that large tidal range here in Hampton. The second plot is the velocity, and we can see speeds reach up over 1 meter per second. And that primary max occurs during the ebbs. This is really ebb dominated. The secondary maximums are occurring during the flood. And finally, we can see the velocity to pressure variance ratio normalized by the gravity wave index defined by my advisor here. And when R is much, much greater than 1, the infragravity band is dominated with horizontal rigid lid-like motions. When R is equal to 1 or less, then the infragravity band is dominated with gravity motions like edge waves and leaky waves. So here, for the most part, throughout our array, throughout our deployment period, we have horizontal rigid lid-like motions, except for sometimes on low tide when it dips down. So I'm going to be talking about 2 different runs. One's a flood tide, and then one's an ebb tide earlier in the time series. So starting with the flood tide, we're still looking at station 3, but now we're looking at the pressure in the top plot and the cross and along channel velocities in the bottom plots, both of which have been quadratically detrended to remove any of the low frequency noise associated with the rising or lowering of the tides. For this run, we're using stations 2 through 5, which shortens our array length to 101 meters. So again, we're not including station 6 and 7 due to those coherency concerns. So we need the IMLEs in order to estimate wavelengths that are longer than 101 meters. But first, looking at this, we can immediately see oscillations in the velocities on the order of several minutes. And this is falling right into our infragravity band, which we can also see in spectral space. So we have the spectra of the velocities and pressure in the top plot, which we see high energies, again, at these low frequency motions associated with those oscillations on the order of several minutes. And again, we have the R ratio down below, which is much greater than 1. So again, we're assuming these motions are rigid lid-like and consistent with instabilities. So using those IMLEs, we're able to use stations 2 through 5 altogether to then generate the estimated wave number frequency spectra of the velocities. So here we see high energy at these low frequencies associated with negative wave numbers in this case. And negative wave numbers indicate an eastward propagation of instabilities, which matches the flooding current direction. So these instabilities are following that mean current direction into the inlet. They fall along a nearly linear dispersive line, and from that we can actually estimate the phase speed, which is about 0.4 meters per second. And assuming that the maximum velocity is between 1 and 1.5 meters per second towards the middle of that inlet, that's roughly 30 to 40% of the max velocity, which is consistent with what our theoretical predictions came up with. You can also see these motions are clearly distinctive from the low mode edge waves, which are the white dotted lines, and the leaky waves, which are the solid white lines. So now for the ebb case, again, we're kind of stepping back in time a little bit here. So station 1, the battery was working, so we were able to include this in the array length, which lengthens our array a little bit, but we're still not using station 6 and 7 for coherency concerns. And again, we're using IMLEs to estimate the wave number frequency spectra, and we're seeing energy at these low frequencies, but now we have positive wave numbers, and that's associated with a eastward propagating direction, which corresponds with the ebbing currents moving out of the inlet. Again, these motions fall along a nearly linear dispersive line from which we can estimate the phase speeds, which are a bit faster in this case. And these motions are clearly distinctive from the low mode edge waves again. So we can compare the observed motions to our theoretical predictions. So here I put in inlet geometry parameters that simulate Hampton Inlet, and then ran our theoretical model. And on the right-hand side, we have the real frequencies in the top plot and the positive imaginary frequencies associated with the instabilities on the bottom right plot with the unstable wave numbers. So here we have the frequencies that we're looking at in this bottom right plot do in fact correspond with what we observed, as well as the wave numbers. Our phase speed of 0.34 is calculated from the real component of the radiant frequency associated with the fastest growing mode. It's a little bit slower than what we observed. So in conclusion, the presence of shear instabilities of tidal currents were observed using a spatially lagged array of current meters. They show progressive characteristics and propagate in the direction of that mean current and are clearly distinctive from the low mode edge waves. The velocity to pressure variance ratio show the infragravity band is dominated with rigid lid-like motions, consistent with instabilities, and the range number of wave numbers and frequencies observed matches and is consistent with those using the theoretical solution. Okay, for chapter 3. We're going to utilize a numerical model that solves the 3D momentum equations to determine the forcing dynamics leading to that observed velocity intensification over the shelf at Henderson Point in the Piscataqua River. So to give some background, Bowen in 1969 looked at the depth average circulation in the near shore and determined, using the potential vorticity balance, that the seaward going currents were intensified under high Reynolds number conditions. So Reynolds number represents the inertial terms to the viscous terms. So when the viscous terms are weak, the Reynolds number is high. So the flow was intensified, which helped explain rip currents. So here we're going to use similar methods using the potential vorticity balance to help us understand what's going on over that shelf. But again, we're applying it to estuarine conditions where the flow is driven by the tides. And we're take it one step further and use ROMs to solve the 3D momentum equations. And this will help us better understand the forcing dynamics. And I think this is not just a single case study here at Henderson Point. I think this can be applied elsewhere to other topographies and bathymetries that have similar forcing conditions. So just to orient everybody, we're looking at the flow south of Seavey Island in the Piscataqua River, which is part of the Great Bay Estuary in New Hampshire. And again, these are Tom and Martin's observations from 2015. And we're really interested in that flow along Transect 1 that shows the fastest currents over the flood, which is the green arrows, and the ebb, which are the magenta arrows, over that shelf, and not necessarily over that deeper channel, which you can see in the top left photo. So we start by deriving a Reynolds number for our situation here, following Bowen's potential vorticity methods here. So we have, again, assumptions about the flow. We're going to neglect Coriolis force, because our depths in our estuary are well within the Rossby radius of deformation. We're neglecting surface wind stress. Our flow is incompressible, so we can reduce our continuity equation. And again, we don't have wave forcing, so currents are driven by the tides here. So we start with our depth average momentum equations for the mean current, where acceleration terms are on the left, and we have a tidally induced pressure gradient, a linear bottom friction, and a horizontal eddy viscosity. We're able to introduce a stream function to represent the velocities. And again, when we plug that into the cross-differentiated momentum equations, we get down to our governing equation here, which is the potential vorticity equation, the nonlinear potential vorticity equation for steady mean currents. You'll notice the right-hand side is not equal to 0. Because we included a bottom friction and a horizontal eddy viscosity, this is not conserved. So we're able to non-dimensionalize this using characteristic length scales L, velocity scales U, and depth scales H in order to ultimately get down to our Reynolds number here, which again shows the inertial terms in the numerator to our viscous terms in the denominator, made up of our linear bottom friction and horizontal eddy viscosity. So we can toggle our Reynolds number between high and low conditions by changing our friction coefficient in our model runs. So here I have 4 model runs, 2 for the ebb flow and 2 for the flood flow. And as I change that friction coefficient, I'm getting different Reynolds number conditions. and that's what I'm observing to see how the flow adjusts to that. So I'm using ROMS, the Regional Ocean Modeling System, and I have a relatively small domain and high-resolution model of a 5-meter horizontal grid with 10 vertical levels, and I have a no-slip condition on the sidewalls, and I'm conserving volume here. My northern and southern boundaries are closed, and my eastern and western boundaries are either clamped or allowing for radiation conditions, depending on which model run I'm running. So here on the right, you can see my initial conditions. If I'm running an ebb flow case, then I'm allowing the model to linearly ramp up to the magenta arrows, and then I'm clamping those arrows for the rest of the run. And on the eastern boundary, I'm allowing the flow to be radiated out. And then I'll flip it for the flood run, clamping to the green arrows and letting the model radiate the flow out on the other end. So because I'm clamping the flow, I'm trying to simulate steady or quasi-steady currents and keeping U not changing too much in time. Meanwhile, I'm also, again, I've already talked about how I'm changing the lambda, the friction coefficient here, to change my Reynolds number. And then I'm going to leave my horizontal eddy viscosity coefficient alone. I'm going to set it as small as possible while maintaining numerical stability, but we're not going to use that in adjusting our Reynolds number because it's primarily used to parameterize the flow, while the friction is a more physical quantity that we can measure. So again, we have the observations at the top left. The bottom left shows the observation lines in red, and then the lines I'm about to show are in yellow from the model runs. They don't perfectly line up. However, the model does do a good job of reproducing the flow. So we have the high Reynolds number case in the top plot, the low Reynolds number case in the bottom plot. We have the flood flow in the green, and the magenta is the ebb flow. And for both the high and low Reynolds number case, the ROMS does a fairly decent job of reproducing what we observed, including areas like this recirculation cell here that's also observed up here. And the most important part is that ROMS was able to simulate the flow being intensified over this shelf, which is what we're most interested in. So here, just looking at the ebb current flow, you do have an intensification of velocity over the shelf. And if you are looking at just that area and just that transect, there is a slight difference in your velocity gradient in your long channel velocity as well, but it might be hard to quantify whether the flow is actually getting faster here. So we can look at the velocity magnitude in the high Reynolds number case versus the low Reynolds number case and actually take the difference. And what's interesting is that the velocity does actually increase in the high Reynolds number case, specifically over the shelf. So all we're doing is changing our friction, which is spatially uniform throughout the whole model, and in turn, we are increasing the velocity over this shallow shelf here by about 0.2 meters per second, which is corresponding to about a 13% increase in our max velocity. So going back to thinking of, well, what are the forcing dynamics causing this intensification? Again, we use the potential vorticity equations to derive our Reynolds number that has the inertial terms to our viscous terms. So we can do a force balance here, just to a scaling argument to see what is the primary force here. So immediately off the bat, we're going to assume that the horizontal eddy viscosity is small relative to our linear friction. So we can cancel that, and now we're going to compare our inertial terms to our friction term. So our inertial time scale of motion is about 3 minutes. And our frictional spin down time, or the time it takes for friction to fully slow down the water, is over 3 hours for a moderate friction coefficient. So this is kind of in between my high and low Reynolds number coefficients. So our inertial timescales of motion are much faster than our frictional spin down time. So here we're saying basically the flow is highly inertial. If the flow is inertial, it's going to move over that shelf, and that area is going to be smaller. So just due to conservation of volume, it's going to increase, right? From this scaling argument, we could also argue that my governing equation of potential vorticity, which had a bunch of terms on the right-hand side with eddy viscosity and bottom friction, I just said that they're small. So if they're small, we can almost approximate the potential vorticity as being nearly conserved. If that's the case, then if there are changes in depth here, then the relative vorticity has to change in response. So it's another way to think about what's going on here. Just wanted to show the flood current case quickly. It also shows, obviously, the currents increasing over the shelf, but it also shows the currents increasing in this other shallow area as part of our domain and not having fast currents in that deeper part of the channel like maybe we would expect. So this gives a little insight into maybe this isn't just a single case of the shelf at Piscata or off the Henderson Point. Maybe this could also be applied to other areas with similar topographies, bathymetries, and forcing dynamics. At a time. I included this video of potential vorticity on the flood case basically for fun. So I'll let you watch and we can talk about it. You will see the model slowly spin up over time. So my model starts at 0. At an hour, it has now the clamped conditions. So you will see we have essentially clamped conditions. I'm trying to impose steady or quasi-steady currents coming in. The flow is adjusting to the topography and the bathymetry. There is some spin-off from the sidewall frictions. We have a no-slip condition. And the flow does ultimately become unsteady and produce these vorticities and eddies, which I talked about in the first chapter. There is a bit of a flow separation off the point, which I won't get into, but if there are questions, we can talk about it. So implications of this, again, I just showed that the flow does in fact become unsteady. And in the first 2 chapters, we talked about how that can lead to a mixing of momentum. So we can actually calculate this in ROMs as well. So now I'm looking at my along channel momentum in the X direction that's being mixed across the channel in the Y direction. And we have a really strong or non-zero Reynolds stress over that shelf again. So again, we're expecting to have really strong horizontal mixing over that shelf in Henderson Point, which can have ecosystem implications. So to conclude in chapter 3, we used ROMs to solve the 3D momentum equations, and we're successfully able to reproduce the observations. Flow is highly inertial, and the velocity is intensified over that shallow area, especially under high Reynolds number conditions. The intensification of the velocity may lead to some instabilities and horizontal mixing of momentum. Okay, so now just to summarize everything, my key takeaways from all of this. The first is that the dispersion of linear barotropic instabilities of mean tidal currents was solved. The solution is 3rd order, it's general, and we can boil it down towards the nearshore solution, which is a great check on our solution. Second, the presence of shear instabilities of tidal currents were observed with little to no wave forcing. So again, we're hypothesizing that this is driven from the shear of the tidal currents and not necessarily from the wave groups. The characteristic scales of motions, again, hundreds of meters, wavelengths, frequencies in the far gravity and infragravity band, phase speeds that are on the order of a third of the max velocity are consistent with those predicted by the dispersion equation and also those that have been observed and predicted in the nearshore environment. And finally, the velocity intensification observed over the shallow shelf can be reproduced with ROMs and occurs under high Reynolds number conditions. So this all has implications. The temporal and spatial variability of mean tidal currents all has implications for the fate and transport of organic and inorganic matter, navigation, and renewable energy initiatives. So with that, I would like to take some time to thank a bunch of people. I'll start first with my committee. Tom introduced everybody. And I don't know if everybody noticed, but everybody on my committee comes from a different background, which I found fascinating and interesting and really helpful because everybody came with a different perspective and was thinking about my problems in a different way. So it helped me to also think about it in a different and arguably better way. So first and foremost, thank you, Tom, taking me on as a student, and it's been honestly an honor to work with you, and I've learned a ton from you and also all of you in general. I literally could spend an hour just talking about what I've learned from your classes and also your mentorship, so that I will move on. There's a lot of people to thank here from NOAA, the Advanced Education Program. Thank you to Greg and Marion for spearheading that, getting that going, and supporting me through that. Also Jason chatted, who helped me pay tuition every semester. From OD, my management, Pat, Carolyn, and also my team, CCAT, and Carl's here in the audience. Hernan, who helped encourage me to apply in the beginning. Peter Stone, who had support from the R&D board, and Eddie Rogenstein, who juggled field schedules with me to get all of our field work done simultaneously with this. From UNH, the SEPS Fellowship supported me in my first year, which was really critical. The Advanced Education Program wasn't running yet, so that actually was very critical in getting me going. And then the oceanography department covered my last semester. So thank you to SEPS, my department at Sue Clark, for helping facilitate that. The School of Marine Science and Ocean Engineering helped fund our graduate student, our research, basically all of our fieldwork was funded by SMSOE. So a big thanks also to Diane Foster, who lent sensors and equipment to us, and Katie May, who helped with the purchasing. Thank you to everybody who helped us in the field. So John, Jang, Josh, Savannah, Spencer, Melissa, and Jane. It was pretty cold water in May in New Hampshire, so I appreciate everybody going out multiple times to deploy and recover our sensors. And finally, CCOM-JHC, Andy Armstrong, who's here. Thank you for letting me borrow the Suburban to drive down to Delaware a couple times. I'm so glad it didn't die on me. And Will, IT team, Chris, obviously here, and obviously all the admins. Thank you, everybody here. And then last but not least, thank you to my friends and family. Might be a little hard to see the yellow, I apologize, but current and former students at UNH here, both in the oceanography and ocean engineering program. It's a really special cohort where a lot of people come from different backgrounds and different stages in their career. And so it makes for a diverse group of people to both do research with, but more importantly, to be friends with. So thank you all. So with that, I will take questions.
Thank you, Katie. So at this point, we can open up questions to the audience or anybody online, and then the committee will meet with Katie after.
Annie.
And what you just.
Okay, that was heavy. You did a really good job.
Sorry.
Way over my head. But I come from the background of more of an environmental standpoint. And so in the real estuaries, you're going to have marine debris and you're going to have all sorts of biology on the seafloor. So does that impact these results at all and the assumptions you make? It seems like you kind of assume that they're not there.
Yeah.
If you were to include them, would it like change any of your results or how you could apply these?
Good question. Are you talking about marine debris that's floating and getting evicted?
No, basically anything on the seafloor that would screw up your.
Not really, because for the most part, we're depth averaging our currents here. So we're not really accounting for that bottom boundary layer necessarily, where the flow could be different, right? Because of all the vegetation and anything else on the seafloor. So the easy answer is no, we're not accounting for it. We're depth averaging the flow. The hard answer is I don't know if you were to maybe take just the bottom boundary layer and run this analysis, if that would produce different results. I imagine so, because the velocities would be different. Does that answer your question?
Kind of. I'm just thinking, like, if it's big enough, right, the channels change shape over time.
Right.
You know, like all sorts of things are actually dynamic
Yeah.
in the real environment. So like, does this model work like you go out, you make your measurements, it works like once, or do you have to like do these like every 4 years or?
Yeah, I mean, I guess it depends how dynamic the estuary is and how often those changes are happening and how significant they are, right? Like, would they be an order one change because there's a little bit of silt versus the Army Corps dredged a whole channel and now it's totally deep, and I feel like it would depend. If the changes are small, I think the predictions would still apply and the observations would still apply. If the changes are large, like dredging or widening or something that would create a larger change in the velocities, then you'd have to remeasure it. Yeah, well.
So kind of in the same vein, but a little bit more in the physical realm. Because you're doing these in estuarine environments, how would stratification play into it? You said that they were well mixed, but
Yeah,
it's
so
not necessarily always the case.
It's a good question. I skipped right over that. These are barotropic instabilities. I'm depth averaging. We have well mixed environments. I didn't even show the velocity with depth. Actually, no, I did in the beginning, but there is very small change in velocity. But I think that is a good question because a lot of the estuarine literature does look at baroclinic instabilities, especially because of the salinity gradients, right? So where we are, we're so close to the mouth of these estuaries that it is really well mixed. But if you move up into an area where you have a stronger gradient, I think you'd have to do a 2-layer model probably.
Right.
One for the bottom flow, one for the top flow. But there is a lot of work in estuaries that look at the baroclinic instabilities in the vertical. Mine is really just horizontal, so that's a good question. I did not look into it.
Okay.
Yes.
Yeah, I mean, following on from the baroclinic aspect,
Yeah.
downstream of Henderson Point, upstream it is well mixed at almost every phase of the tide, but it does become extremely stratified there. And if you depth average, as you go into deeper water, you're kind of biased.
Right.
But the other thing I noticed, and I think you pointed it out, that big trapped eddy on the other side of Henderson Point, isn't that automatically going to slow things down, and that alone could sort of describe why it's going fast over there? Well, the one on the south side,
This one,
yeah, because if that's going backwards, and it is in my little rowboat, it is,
yeah.
won't that, how general is this? Because Henderson Point is artificially blasted, it's a corner,
Mhm.
and you've got this trapped eddy, and that makes it slow anyway. So doesn't that dominate? Or, well, I guess the more general question, if you straighten the estuary, do you think it would still happen?
Is a good question if I straighten the estuary. So this started with me doing idealized models with just a straight estuary and a bump. And then we then applied it to more realistic topographies. I'd have to go back and look at that. I still think that when we look at just the velocity, the depth average vectors, the vectors over Henderson Point are still stronger than this. This is potential vorticity, not necessarily velocity. And so,
Slide 10 has, I think, velocity.
sorry,
Slide 10.
Slide 10.
Is your, I think it's slide 10. I got it right. Yep.
here's at Henderson Point. Do you want to look at the depth average current?
Yeah, the one with the purple and green.
Yeah,
It's up here.
but that should.
Nope, that's Hampton.
Slide 10.
Here we go.
Yeah.
I mean, that's just
So
beginning to see that.
Yeah, we're missing the
What's in there?
observations, what's in there.
But that's also very shallow water, isn't it?
Yeah.
Yeah, yeah, I mean, it's,
You can see by the yachts, because the yachts tell you where the contours are. It's amazingly deep up to the mouth of Little Bay there.
Also in the upper part of the estuary, in that figure on the left, the left figure there, you showed intensification over that shoal.
yeah.
There's no
Over.
eddy on the other side. So it didn't seem to have any effect on that, at least.
Yes, Andy.
So when they blew that area up
Yes.
100 years ago or so, do you think they got it right or what they expected?
Well, it's a hard bottom, right? So nothing is, it's not like sand's moving around, so it's gonna stay how it is, right? They literally blew it up, didn't they, to create that shelf? I don't know if they blew it up with the intention of creating fast currents, right? They had it for ships, right, to deepen the channel to help.
I think they
There's a
did
navy yard
because of the difficulty of navigating that bend.
Oh, really? Oh, I didn't know that. I thought they were just deepening it. Oh, that's interesting. Well, yeah, I don't know if it created a harder problem for mariners than if they just made it. Carl has a boat there. Has it been difficult to navigate?
Well, not on my boat.
How much did they take out? I'm not sure. How much did they take out? Do you know how much rock they removed? How deep how much did they deepen the channel?
10 feet maybe? It was the largest man-made explosion up to the
Would you
time.
expected that 10-foot change to have an effect on your results if you've got a 35-foot depth? No?
Well, the shelf was what they blew up, right? Yeah.
I feel like a 10-foot change would have, well, I guess I'm thinking meters instead of feet.
Yeah, I don't know, can you hear me out there?
Hi, yes, Larry.
This is Larry, yeah, they went from about 7-8 meters to 11. I think it's pretty flat at 11 meters now. And it was definitely for navigation purposes. They used to call that dead man's curve or something like that, because they had such difficulty getting around that bend.
It's good to know. Need to read more about that story, clearly. Yes, John.
Katie, you mentioned that this intensification of these shallow shoals could probably be present elsewhere, given the same kind of forcing, same bathymetry or similar bathymetry and topography features. So based on your experience in co-ops, what would be potential areas that might have the same intensification?
It's a good question. I think we need to do a better job of utilizing our models and also doing more ADCP transects ahead of going to deploying our current meters, which now we've started to do. We just got a new Nortec VM system, which we can use as a reconnaissance tool. I think before we were pretty much just looking at the charts. Our reconnaissance was more of, if there was a model, we could look at it, but if there wasn't a model, we're just using our best guess. That doesn't sound right, but Carl, you can correct me.
Well, and historical locations
Right.
and pilot input.
Right.
So, yeah, it's all that.
But now I think if we have the ADCP, that we can do those cross-inlet transects, we can get a better sense of that spatial variability before we put equipment in and before we decide what the best location is. We just have to do those transects on both flood and ebb at an idealized time, right? Not just spontaneously. It's Jeffrey.
So since people are talking about dredging, I'm curious, based on your chapter 1 results, I think you said the wider the shelf gets, the more it favors instabilities, but then the deeper it gets, the less. So if we dredge a ship channel that's deep and narrow,
So
do those forces or potential components cancel out?
no, so if the channel gets wider and deeper, then you have faster growing modes. So, but that's just of the deeper shelves, not necessarily of the channel itself. So if you have a deep channel, I can play with actually changing the depth of those channels too, to play with it. But really I'm just looking at the sides of it. So if you have shallow shelves that are wide, yeah, I'd have to look at the magnitudes to see if shelf depth or width is the stronger component to see if they would cancel. But you're thinking about Mobile Bay?
So the question is, we dredge deep ship channels that proportionally are much deeper and much narrower compared to the width. Do we expect to see instabilities playing a role in how that momentum mixes out, or does it stay conserved because it is disproportionately deep and narrow?
A great question.
Or is
I have
that
to run my
something we can
model.
look in the future?
Yeah, I can run my model and tell you. Give me a couple days.
So you're saying your model is flexible enough to handle situations like that?
Thank you. Yes,
But-
exactly.
But in this case, where you have, like, say, a fixed normalized depth, and you're basically essentially changing the relative height of the shell.
Right.
What happens then?
If you have shallower
You're just
shelves,
changing the relative height of the shell. So
right, then you're gonna have slower growth rates
slower growth rates.
and smaller wave numbers, so longer wave
Presumably
lengths.
because you have more of the channel constrained with that.
Yeah. Yes, Peter.
So one of your conclusions here was that these motions are very much inertially dominated. How do, and NOAA does a lot of dredging channel maintenance out in the ocean, on the ocean side through the tidal deltas. How does that dominance of inertial motion, does that feed back into how the tidal deltas, flood tidal deltas evolve? Or, I mean, that's kind of outside what you were looking at, I understand, but do you have a feel for that?
Yeah, I'm assuming if you're dredging an area, it's good to have an impact on the velocities, right? But if you're dredging it, you're making it deeper, which I assume would then mean you're gonna have less influence from bottom friction, and so you're lowering your viscous forces and increasing your inertia. So I assume you're actually making it more inertial if you have a deeper channel.
So do you think that will increase or decrease sediment transport out on the tidal shoals, or either set of tidal shoals?
If you have faster velocities, given the same type of sediment, maybe increase, because then you are more likely to reach incipient motion. Diane?
I'll say Katie.
I think so. I think it would increase it. Any other questions? Oh, yes, Melissa.
So now that you've done chapter 3, the numerical stuff, if you could run a field experiment again, is there anything you would change? Assuming you had infinite time and money
Yeah, so
and all those things.
Yeah, I didn't show it, but I do have virtual stations in ROMs right along here, and I did an instability analysis there, but it would be cool to actually deploy equipment there and compare my ROMs instability analysis to observations. I don't think that's really feasible given the navigational channel there, but would be nice.
I'm just curious.
Expand.
Yeah, right, yeah, I could do it without actual in situ.
Okay, are there any other questions? Anything from the chat or anything? No? All right then. Thank you all for coming.